Hello everyone, I'm Shou-Fu Tian and currently working at China University of Minery and Technology. Today, I will report on the latest progress of our research group. The title of my presentation is Certain Resolution for the Complex Short Plus Equation with weighted Sobolev initial date. This work is joined with my two PhD students, Tian, Jin Jieyang, and Professor Ngui Fan. He is working at Fudan University. Next, I will make my presentation from the following aspects. First, let me introduce the development of the certain resolution conjecture. As we know, the certain phenomenon was first discovered by British engineer Shou-Fu in 1834, and the concept of a certain can be tracked back to 1965. After that, Zabatsky and Kraskov observed that any numerical solution for KTV equation breaks up into the sum of several certainties. In 1978, Professor Lux thoroughly proved a simplest case for T. The solutions of KTV equation behaves as the superposition of two solitary waves traveling at different speeds. In 2008, for NRS equation, in the radial case and in the high dimensions, Professor Tao proved that the certain splits into linear dispersive part in the phi field and a local part which belong to a compact attractor. At present, people believe that for general dispersion equation, one has the same universal behavior for that time. Mathematically, this is called the certain resolution conjecture. The certain resolution conjecture refers to the properties that the solution decomposed into the sum of a finite number of separated certains and a radiative part as time t tending to infinity. At present, for the completely integrable equations such as the Werner KTV equation and NRS equation, the certain resolution conjecture of them can be solved. While for non-integrable equations, it has not progressed well. In order to better study the certain resolution conjecture, the D+D-based descent method is gradually applied and developed. In recent years, the definite descent method is further extended to the D+D-based descent method by McLaughlin and Miller to analysis asymptotic of signal polynomials with non-analytical ways. When it is applied to integrable systems, the D+D-based descent method also has displayed some advantages, such as avoiding delicate estimates, avoiding LP estimates of quasi-product operators, and improving error estimates. In integrable system, applying the D+D-based descent method and the definite zone method, many works about certain resolution have been given, including Kukana, Yamani, Jenkins, Burhouse, and other researchers' work. However, there are very few studies on the certain resolution conjecture of a negative order flow equation in integrable, and on finite there's certain initial value condition and so on. Our group studied the certain resolution for some negative order flow equations, including WK equation, complex short-plus equation, and Thomas-Helm equation. For example, we developed the deep-based Darcy method to study the certain resolutions of the WK equation. Its phase function admits one steady-state phase point. Furthermore, we studied the complex short-plus equation, whose phase function admits multiple steady-state phase points. We also studied the asymptotic stability of uncertain solutions for the WK equation. Next, I will report some results of the complex short-plus equation. This equation was proposed by Shou-Fu and Wang in 2004 for describing the propagation of ultra short-plus in spherical optical fibers. The short-plus equation can be viewed as the short-wave approximation to the modified Thomas-Helm equation. Since the short-plus equation was proposed, a series of works have been reported, including WK-type Lux pair, B Hamiltonian structure, the conservation laws, global wire-pushness, long-time asymptotic behavior, background transformation, certain resolution, and several other work. Unfortunately, the one-third solutions of the short-plus equation has no physics interpretation. Feng studied complex equation, complex short-plus equation in 2015. After that, Feng and his co-workers Lin and Zhu studied its multi-sorting, multi-birthing, and high-order log-wave solutions. In 2020, Xu and Fan reported its long-time asymptotic behavior by using the nonlinear steepest Darcy method. There is a natural question: how about the certain resolution for complex short equation? In this work, we developed the deep-steepest desert method to study certain resolution for the complex short-plus equation. Next is the initial value problem of the specific complex short-plus equation. Its initial value belongs to a weighted Sobolev space. This space can be strictly drawn. Our purpose is to study the certain resolution for the solution U of a complex short-plus equation as time t tending to infinity. The space is derived from the skirting coefficient R belonging to each one space. Next, we constructed the corresponding H problem from the lattice pair of this equation. This equation has a lattice pair of this form. Unlike the AKS type lattice pairs, the lattice pair of this equation has singularities at z equals to 0 and z equals infinity. Therefore, we need to consider the properties of edge functions at 0 and infinity respectively. First, when z is equal to 0, the transformation is introduced and the original lattice pair can be transformed into the following equivalent form. Further, we can rewrite the equivalent lattice pair in the form of one differential closed form, as so to obtain its virtual integrable equation. According to the virtual integral equation, we can analyze the analytical and asymptotic properties of the edge functions mu0, plus and minus. For the case of singularities at v equal to infinity, we defined the matrix G and other parameters, and then introduced the transformation 11. Similarly, original locked pair is transformed into equivalent locked pair that can be written in four differential form, and then the corresponding virtual integrable equation can be obtained. According to this virtual integrable equation, we can obtain the analytical symmetric and asymptotic properties of edge functions mu plus minus. It is worth noting that, compared with the real-valued surplus equation, this symmetry is missing. The red fit. Moreover, because the function mu plus minus are the solutions of the corresponding locked pairs equations show, this exists the scaling matrix S, making the edge functions mu plus minus satisfies the following relationship 16. Then, according to the properties of the edge functions mu plus minus, analytical symmetry and asymptotic properties of the scaling matrix S can be drawn. In addition, the edge functions mu plus minus and mu 0 plus minus satisfies the following relationship 18. At this point, in order to establish a suitable edge problem corresponding to the case problem of the complex short plus equation, we make two asymptotics. These two asymptotics, and define a matrix function M tiered. Then, the original problem can be transformed into the RHP problem. This is RHP problem. Find analysis function M tiered with the following properties. In order to reconstruct the suitable expression for the solution U of the original equation, we need to study the asymptotic behavior of M when they tend to 0. From equation 22, we can see that there is an integrable term in the expression of C plus in 22. It will cause some troubles for our later analysis. Therefore, we further introduced the transformation 23 to get a new edge problem, HP2 for M. According to HP2, our recovered partition U can be expressed as equation 26. Next, we will consider the asymptotic behavior problem. We first analyze the symbol table of the phase function. According to the assimilation term of the jump matrix, we found that phase function has two steady state phase points, plus minus C0. The declining region of the real part of the phase function is shown in Figure 1. Next, we introduce the T function to redistribute pores and remove the diagonal factor. By introducing delta function and T function, we defined a new function M1, and the HP2 can be transformed into a new edge problem. We obtained HP3. The equation 31 is the residue condition of M1. Accordingly, the potential the potential U can be recovered by M1. Next, we introduce the R2 for continuous excitation. Here, we defined a new jump counter sigma 2 thing. The complex plane C is separated into 10 sectors. The original jump path is extended to 12 steepest descent lines. We introduced the transformation 13.2. We can get an algebra problem about M2, which is a mixed D-bar problem. How to solve the mixed D-bar problem? We can divide it into two parts. D-bar derivative is equal to 0. D-bar derivative is not equal to 0, and record them as M2 HP and M3 respectively. For M2 HP, we further divided it into external and internal near small neighborhood of steady-state phase point, which are respectively recorded as M out and MZ 0. For M out, introduced the transformation 33. We can see that M out satisfies the RHP problem of the following RHP 6. We can use the Soliton solutions obtained by finite discrete spectrum in a geometry figure structured by space-time coin to approximate the solution of M out. The error function is exponential decay, and obtained the result present in proposition 1. Throughout this method, we solved the M out problem. For the internal of the small neighborhood of the phase point, M2 RHP is reduced to the following RHP problem, RHP 7. This is the corresponding jump counter. This RHP problem can be solved by matching the parabolic sliding model. The following is the RHP problem, satisfying the standard parabolic sliding method. This is the corresponding jump counter. This is the standard solution for the PC model. Unlike the process of storing real-valued short-plus equation near the phase point, MCSP does not admit the symmetry condition. Therefore, we have to use PC model to solve the problem near the two phase point plus mu 0 separately. Then we obtained the solution of MCSP further. The solution of MZ0 can be obtained. Next, we will study the error function E. Actually, E satisfies a small normal RHP problem. According to the analysis above, the error function E can be expressed as equation 41. Then we find that the error function E satisfies a small normal RHP problem, RHP 9. Actually, this RHP problem is solved. This is the corresponding jump counter. Then we can get the solution about E, including E0 and E1. In what follows, we solve the part where the derivative of D bar is not equal to 0, that is M3. M3 satisfies the following problem, HP10. By analyzing this HP problem, we can beat the estimate of M3 when t tends to infinity, shows in equation 14.6 and 14.7. Finally, recall a series of transformation process, including M1, M2, M3, and E. We can get the expressions of M, especially we take the tending to 0 along the imaginary axis. Then R2 is equal to an identity matrix. So finally, we can get the expression of M0 and the inverse of M0 times M. Then from the reconstruction, we beat the expression of the potential U. From the expression of U, we can see that the certain resolution of complex short plus equation is solved now, and the results show that the complex short plus equation has the certain resolution phenomenon. Those are some of the parameter representations. Finally, we give some reference. That's all. Thanks for your attention. 可以了。但是我